Bismillah wa salatu wassalamu ala rasulillah. This is Engineer Areej Abdelaal. Today we will be talking about the quicksort algorithm, and our discussion of data structures and algorithms will be focusing on the idea of quicksort, and we will share one of the implementations. It is not an in-place implementation. However, it's a clear one. And this will not include the performance analysis. Now let's just look at the analogy. Let's assume that we have a class of 5 students, and we want them to order themselves or to sort themselves ascendingly. So the shorter guys on the left and the taller ones to the right. Now let's assume that they will pick one student, let's say always the most right, and they will sort only that guy. That is, the taller people go to their right of that one we selected. Let's just call that one we selected, let's say the guy in green. Let's say this student, we will call this person pivot. And now the taller people will go to his right, and the shorter people will go to his left. So by sorting only the pivot, the guy in green, we have this person to his right, and we have these people to his left. We notice that the ones to his right are taller, which is actually one person over this example, and we have 3 people to their left, which are shorter than his height. Now, only this pivot, this person is sorted. That is, if you were to ask yourself, who is the shortest person, the first or the second or the third or the fifth shortest person in this class, you cannot guarantee your answer is correct. However, if you ask who is the 4th shortest person in this class, you definitely know the answer. Why? Because you have a pivot sorted at the index of the 4th element. Let's continue. Now we go to the pivot's right, and we don't have somebody to compare him to, which is only one person in the orange box. So this one is already sorted by nature because there is no one to compare within this orange box. Now let's go to the left side, the blue box. We have 3 people, so we have someone to compare to. We will pick the rightmost person, now the one in green, and this becomes our new pivot for this part of the class. Now the people taller than him will go to his right, the people shorter than him will go to his left. We notice that all of the people happen to be taller than him, so all of them go to his right. Now this pivot is sorted and we are done with them. That's it, we're done. Now we pick people to his right and people to his left, and we just repeat the same cycle again. It happens nobody to their left, which is good, so no one over here, which is good, so we're done. The ones to his right are in the orange box, the inner one. And we do exactly the same process. Pick the rightmost person, this girl, over here in green, and we compare everybody to her. It happens to be that the remaining people, which is the student over here, the shadowed person, happens to be the same height, so they don't need to switch. We're done. Now, everybody is sorted. Everybody happened to be a pivot or remained alone in a box. This is what quicksort is about. Quicksort is not the fastest sorting algorithm, but it is a quicksort. Now, the performance of quicksort is affected greatly by how we select the pivot. For the sake of this video, because we're explaining an idea, we will stick with selecting the pivot to be always the rightmost of the given array we are working with, right? And when we take a partition, we will take the rightmost of that partition. We start with an array. We select the pivot to be the rightmost of this array, and we sort that pivot. It happened to be right here. The smaller elements goes to the pivot's left, and the greater elements goes to the pivot's right. For the left part, so over here, this becomes its own array, and we do the same process again. We select the pivot to be the most right of it, which is the 20. We sort it, and then we are done with the cycle. We will then continue to pick the remaining ones on its right and the remaining ones to its left. Here, no, nothing is on its left. And we pick these as our new arrays to continue our recursion tree. And for this side, we will include the pivot in our implementation. Now, typically, you don't need to do that. You simply don't need to do that. There are other implementations, but for the implementation we are working with today, we will take the pivot with us on the right side, recursive call. So the 70 is going with us, and the new pivot is this guy over here, and we will sort. This may add a little bit of extra steps. However, the general implementation is going to be clear enough. Now let's look at the quick sort process. The quick sort, or whatever we have, you will start with an array, you select the pivot and you sort it, then you go for its left, do the same process, go to its right and do the same process. Selecting the pivot and sorting it is included within a process that we call partition. The recursive part is to select a partition or to partition things around a pivot, then quick sort whatever before that pivot, and then quick sort whatever after that pivot. Which means our recursive part is this. You have partitioning process, then you have the quick sort call for the left side and the quick sort call for the right side. What about the base case? If we have a recursion, then we need a base case, some way to stop the quick sort recursive calls, which is going to be this. If you have the low equal to the high, which means an array of only single elements, you're starting and ending at the same point, you stop. Now, I do say if you have an array of a single element, but most likely we won't. Most likely we have an array of multiple elements. So what does the low and high mean? It means the starting and the ending of whatever partition we are working with. At the very beginning of your call, the very first call, you are working on the full partition. That is, your low is 0, the first index over here, if you are doing Java, and your high is the array.length, -1, if you are doing Java again. So you end up at here. This is your first low, and this is your first high. Once you partition, you have a new low and high for the right side, and you have another low and high for the left side. For the left side, we will take the new low as the same older low, right? Because this is the beginning of the left side to the pivot. However, it ends with whatever pivot you have -1, so the index right before that. And for the right side, we will take the pivot with us to be our low, and then the high will be the ending of whatever array we just started with, whatever partition we started with. And this recursive tree will keep going. So this is the recursive part of the quicksort. Now, the difficult part is not really with the quicksort recursive process or method. The problem comes with the partitioning, because partitioning is where the magic happens. Though this part, the partitioning over here, it is not recursive, but it takes some effort to implement. There are different ways to implement it. We will pick today one of these ways. So let's start over here. We will start with an example called, let's say, 2, 5, 1, and 3. We should be ending up with 1, 2, 3, and this 5. This should be our result. So let's start with 2, 5, 1, 3. This index 0, 1, 2, and 3. This is the first low, and this is the first high. So our logic of partitioning is using 2 pointers, I and j. I starts with the low, j starts at the high. I should always represent the values left to the pivot. that is smaller to the pivot. J should always represent the values greater than or equal to the pivot. So I should be for the smaller side, and J should be for the greater side. Of course, we will pick only one of them to represent the equal, so I will pick this one, greater or equal. And how we proceed is that we select the rightmost value of whatever we have, which is originally at high, and then we will increment I until we reach a value violating this condition. Then we will decrement J until we face a value violating this condition. So let's do it. I will increment. It's now at 5, which is violating the smaller condition. 5 is not less than 3. But wait, we just faced the trouble. We started with I at 2, but did we check the 2? No, we didn't. We did not check the 2. So again, let me just repeat that. We will increment I until we face a value that is greater than the pivot or equal to the pivot, so not smaller, violating the smaller condition. One way of handling this, especially with a do while loop, will be by adding a value as a definitely lower value than whatever I is. That is, let's remove these indices and let's over here add a minus infinity. So now I doesn't start at this, I starts over here. What is this? It's a definitely smaller value than the pivot. So we're always starting with this. All right, so now this is our 0, 1, 2, 3, and 4. This is our actual low. Now, because we are adding a value to the array, and it's array, so you don't really add values, you need to create another array with a greater length and then add this minus infinity. That means we are not doing an in-place quicksort per se. I hope this one is clear. So now we have a minus infinity. We increment the I automatically without checking it at minus infinity, and we face a 2. Is 2 smaller than the pivot 3? Yes, it is. So we will just increment the I once more. Now over here, is 5 smaller than the 3? No, we just violated the I's condition, so we stop I over here. Now I is stopping at a greater value or equal value to the pivot, something that violates this condition. Now let's move on to the J. J immediately decrements. So over here, it's now at the value 1. Is 1 greater than or equal to the pivot 3? No, we just violated the J's condition. So we stop the J over here. That's it, we just stopped. Now we know that J stops at a value smaller than the pivot, and the I stops at the value greater than or equal to the pivot. That is, whatever the values at I and J, they need to swap. So we swap the values of I and the values of J. Now what we have is minus infinity, 2, 1, 5, and 3. I is still at this point, J is still at this point, and this is still our pivot. So we move on. Increment the I as long until you face a value violating the I's condition, the smaller condition. So we increment the I. We find a 5. Is 5 smaller than 3? No. Stop I. Decrement the J until you face a value not greater than or equal to the pivot. So here we go. We face a 1. Is 1 greater than or equal to the 3, the pivot? No, it is not. You stop the J. Now we have some weird thing. I and J just crossed. What does that mean? It means that all the smaller values than the pivot are already done. We just made the j, which are the greater ones. So now we need to stop our loop and we declare where I stands as the new pivot. This should be the place of the previous pivot, and we swap whatever the value at I with the pivot. So if crossed, that is, if I is now greater than j, we need to break our loop and we swap whatever happens to be at I with the pivot. So it's basically the A of I. So now we have this situation: minus infinity, 2, 1, 3, and 5. Remember that 3 used to be the pivot, but now we don't really have a link to it. We don't know. The only thing we know is this is where I is now standing. So this is the pivot sorted. And this is where the partitions will end and start for the next quicksort recursive cycle. So now we simply return the I as the new pivot index. Now let's just make some difference over here. Over here we swapped I with an j because there was still a room for I to be in its place and j to be in its place. That is, I was still less than j. We can still continue our loop of getting all the smaller ones before and the greater ones after. Once they crossed, we know for a fact that all the smaller ones have finished and we just started the greater ones. All the coming will be for I will be all greater because j has crossed all this part already. So now just go back and take a look at the code. Here it is. We define I to be the low, j to be the high, pivot to be array of high. And while I is less than a j, they didn't cross yet, we will increment the I while array of I is less than the pivot. You can simply remove this equal. And we will decrement j while array of j is greater than or equal to the pivot. Within the same loop, if I still didn't cross j and these two loops have ended, that is I and j has stopped, but they didn't cross, we swap whatever at I with whatever at j. If we exit this loop, that is, this condition has broken, we swap whatever at the I with whatever at the pivot. Now this can happen with if condition. And finally, we return this as the new pivot. All right, let's simply code this and move on. All right, here we go. I have a class that I call quicksort. I have a class that I call quicksort and I'm using IntelliJ. So let's simply start with public class quicksort. And over here, I will have a public, I will go with a static method. This one will be an integer array. It returns the integer array of quicksort. And this takes an integer array, takes an integer low and an integer high. But this will be always the one called first, so I don't really need to have an starting and ending for it. Now, why I'm returning the array? Because I will do some work on it, and I don't want really to depend on the fact that I am changing by reference. I want to be very clear with whatever I am doing and returning. Over here, I will start with an array, and I need to pad it with a minus infinity. Now, I cannot simply add a new position or index to the array, right? I need to use whatever I'm giving. So I will just have a new array. So let's just call it the padded array. This one is a new integer array with the same length of array.length, the given one, plus 1 for the minus infinity. And then I will say the padded array of 0 is the negative infinity which is integer dot minimum value. Then I want to copy whatever inside the array into the padded array, because now I only have the 0 value in it. So just do a for loop. So from I equals to 0, I is less than array.length, and I plus plus. This is the padded array of I plus 1, so the next index should be the same as array of I. So whatever in array, I'm copying it into padded array. Now there is some static methods to do this, but I will avoid them for clarity. Then I will call quicksort on this array. So here we go. Quicksort, but this time I need to use the recursive one, right? And I will be giving it the padded array. And I will start from the 0 and end with the padded array.length -1. And then I will do a for loop, right? So for integer I equals to 0, I is less than array.length, and I plus plus. Now the array of I should be the padded array of I plus 1. Why is that? To remove the minus infinity effect I've just added, and then I'm returning the array I started with. Now I'm not saying that you have to return the array you started with. Basically it will be the same array again. This is how Java handles arrays. However, I'm just doing this for clarity. Now let's have the quicksort recursive. It will be void, and you'll be given a padded array and I and right. Let's just call these things different names. We start with low and we end up with high. So now let's say if low is less than or equal to, greater than or equal to the high, simply stop. We're done. Now, otherwise, we need to have the new pivot. But remember, this is not a value, this is an index, right? And this will be called by the partition method. Partition of this given array with this low and with this high. And then we will call the quicksort recursive over the same array with the same low, but for the new pivot, we will use it -1. And then you'll have the quicksort recur. We have the array, and we will start with the new pivot, and we will go up to the high. What does that mean? It means that always the left side has a lower value, which is the -infinity, and the greater side has the lower value of it, the right side, which is the pivot. It is less than everything to its right. Right. And now let's just do the partitioning method. Yeah, let's just keep everything as is. So this will be integer I equals low and j equals high, and the pivot is whatever at high. Now we don't really need to name array of high into pivot, but yeah, just to use this. Now while I is less than j, let's do I plus plus while array of I is less than the pivot, and also do j minus minus while array of j is greater than or equal to the pivot. And then if you exit both loops while still didn't cross, so if I still is less than j, we need to swap within the array whatever at I with whatever at j. Once we exit the loop, it means we have just crossed, right? So, or we're at the same point. So we will simply swap whatever at array I with whatever at I, which is the pivot's location. And we just return the I. Now, over here, let's create our own method, right? Here we go. So this I will call it I1, and this I will call it I2. So index 1 and index 2. So this is the swapping. And then whatever at I1 should be whatever at I2. And whatever at I2 should get whatever at temps. Right? Yeah, I named on the unit testing, this was with a capital S. This should be it. Now let's try our tests over here. If I have, for example, 2, 5, and 1, I should end up with 1, 2, and 5. Let's run this. And we are good to go. Now similarly, you will notice multiple tests. I test for duplicates and for different edge cases. Now let's run everything. And all of them are working. Now just a final note over here. And the merge sort, which is another way of sorting, the division part is very simple. Go with a half and split into 2. Go to the half and split into 2. For the conquer part, it is where things go rough, right? Because you need to do lots of comparisons and the actual sorting occurs in the conquer part. However, in the quick sort, which is the one we worked on, the divide part is difficult because this is where you need to do the partitioning. As you could see, when we were simply going for the quick sort itself, it was easy. But for the partitioning part, we needed to work around it. We needed to, let's say, use minus infinity and stuff like that. However, for the conquer,